All right, so now we're going to go on to lesson 7.4, reciprocal functions part 2, and this is going to be dealing with what happens if we want to state the original function or come up with the original function given the graph of the reciprocal function at some point. And so what they're going to do is just like the one off to our right-hand side here, we're going to be given some sort of graph which represents a reciprocal, and then we need to formulate what is this original function that would give us this as the reciprocal, or this y equals 1 over f of x. Now, to sketch the graph of the original function, what we're going to do is we're going to pull some interesting and unique characteristics off of the reciprocal that are used to build the original. Now, some of those characteristics are the following. So if I zoom into this graph here, first and foremost, I look at this and I go, well, we know that one of the points on the original graph is representative by the NPV. In this situation, if we have an NPV where x is equal to, in this situation, -1, it means that the x-intercept is going to be at -1 for our line that we create, and so we want to put a dot there. Now, if this is our vertical asymptote that x equals 1, then what we want to do is use the point that they gave us to generate another one of these points, which if they said that on the reciprocal graph it's -2 and -1/4, well, the x value will stay the same, but on our reciprocal function, or sorry, the original, not the reciprocal, on the reciprocal here, we have it as -1/4. On the original graph, it's going to be -4. So I'm going to put a point down to -2 and -4, which puts me right here. Now, we could also put a point, if it looks like here, just by approximation, I see that we have a point that looks to be like it's at roughly about 1/4 for y. If this is 1/4 for y, we could pretty much assume that this will also be from 1/4 to then 4, because we do the reciprocal. If this is at y equals 1/4, a reciprocal of 1/4 is 4. Now what we want to do is we want to sketch in our invariant points, and if you remember from the previous lesson, or part 1, the invariant points are always located where y equals -1, so we're going to put a point right here, and where y equals +1 on the reciprocal line. And now you're going to see that these all line up very nicely. Let's connect the dots, and let's make sure that we put arrows on the end representing that this goes down to infinity and up to positive infinity. And I should classify that as down to -infinity and then up to positive infinity. Okay, here's our original graph, and we call this the y equals f of x. So if you really want to make sure we're being specific, we put our f of x tag next to this one. Now, there's a couple interesting things that come out of this. Not only do we have the general line that represents this reciprocal function, or sorry, the original, not the reciprocal, represents the original of the reciprocal, but we also have a couple key characteristic points that would help us establish the equation. First and foremost, we have a y-intercept, we have an x-intercept, and then we have a couple other points that are in between here. Now, the ones that are not for sure points are these ones here. We're not 100% sure what this is. We're not 100% sure what this is. We know they're at -y, or y equals 1, and -1, or sorry, +1 for this one. So +1 up here, -1 here. But other than that, we know these 3 points are for sure points that we could use. So what I'm going to do is, when they say determine the original function, and we want to maybe do this thing based on the characteristics of the graph, if we use the slope and the y-intercept, well, let's go off to our graph here. We see that the y-intercept is located, and I'll use black here, it is at 0 for x and then 4 for y. We also see that there is some sort of slope, which is representative of, if we do our slope, it's going to be, let's say we go between any 2 points here. I'm going to go between the point up here and the point right here. Then to go from the left point to the right point, I end up having to go up by a certain amount of units. In this case, I go up by 4 units, and I go over by 1 unit, or I run to my right by 1 unit. Therefore, if I wrote out the slope would be equal to 4 divided by 1, which is simply just 4. So now what we can do is we can put these two things together and say, well, if we know that y equals f of x is the original function, and this is a linear line which follows the form mx plus b, well, that means that my f of x for this situation, I'm going to make that a little neater, the f of x is equal to the slope, which is 4 times x, plus the y-intercept. Now, this would be if the slope, or I guess I should say both, but the slope and the y-intercept are very obvious. You could use this method to your advantage, and it might actually help you really easily. Now, the other method which we could do is using our x-intercept and a point method. Now, what we're going to have to do is we're going to have to figure out what the slope is, because that's obviously going to help us again. So we could use any 2 points. Let's say we use the 0 and 4, and then let's say we use the -2 and -4. So we're going to use these 2 points here. Okay, if we were calculating slope using the y-intercept and this point down here, then it would look like the following. We would say m is equal to the y2 in this situation, which is +4, minus the y1, which is -4, all divided by, in the denominator, it's going to be y2, which is equal to 0, minus y1, which is -2. This is going to give us a slope of 8 divided by +2, which is equal to 4. So yet again, we get 4, no surprise, all good. Now what we want to use is we want to use a point to help us establish the equation. Here's what that looks like. We're going to write it as the following. It is going to be y minus y1 equals m times x minus x1, where this form is called our point slope form, where we can take a specific point and get the linear equation based on the point and the slope we solve for. Now, let's use any point we want that's not the y-intercept. So let's just try and use the -2 and -4. This is going to be written as y minus the -4 is equal to the slope of 4 times x minus the -2. When I expand this, this is going to give me y plus 4, which is equal to 4x plus 8, because we know the double negative would make it +2. 2 times 4 is 8. Now, if I subtract the 4 from both sides, we end up getting that y, which is equal to the f of x, is equal to 4x. 8 minus 4 is +4. And we get the exact same solution. So to nobody's surprise, we should be getting the exact same thing here. And you know what I'm going to do is just move this up just a tad so that it looks a tiny bit neater and isn't as condensed. There we go. So again, we get the same equation. Now, if you do not have a conclusive y-intercept, this is probably the method to go, is just to go with the slope-intercept form, just because, some graphs, it's not going to be as easy as just being like, oh, it crosses exactly at 4. It might be a little bit more ambiguous, which in that case, you would want to make sure that you are doing it slightly different than that. Now, what we're going to do is we're going to look at example 2, which is quite similar, but it's going to give us a slightly different set of information in terms of a graph. Now, to solve this one, what we're going to have to do is we're going to have to put together the following. We have to figure out what are some of these original points to state the original function from its reciprocal. We know it's a linear function because anything that has this form as a reciprocal, where it's kind of this reflected kind of bowing look, we consider this to be a linear. Now, what I want to do is I want to identify a couple things. Invariant points, I want to identify the MPV, which is our x-intercept, and then go from there. Now, to do our MPV, I'm just going to draw a vertical line right down this center point here, in which the lines are diverging to positive and negative infinity. Now, I'm going to write in the following, that our vertical asymptote, or our VA, is where x is equal to +3, because this is the line that they're avoiding. Now, what does this mean? We actually have one of the original points. It's along here as the x-intercept. Your x-intercept is the vertical asymptote on the reciprocal function. The other thing we're going to do is we're going to go to +1 on the reciprocal graph, -1 on the reciprocal graph, and this gives us two other points, because we know that these invariant points that occur along these plus and -1 values for y represent some important value. And you know what I'm going to do is, just to kind of emphasize that, I'm going to actually point to these and then just make a note about them. So I'm going to put a dot here, I'm going to put a line to here, and then I'm just going to make sure that we make a note that and say that these are the invariant points. Where more specifically, the invariant points occur when y is equal to +or -1 on that reciprocal graph. Okay, now invariant points, again, by definition, are points that do not change regardless of if it's the reciprocal graph or the original graph. And the reason is because if you take the reciprocal of 1, it's 1. If you take the reciprocal of -0.5, it's -0.5. Now, this also allows us to, based on the trajectory of this and the slope, we can roughly fill out the rest of the points here. And what this means is we're actually going to get a lot of for sure points that are 1 and 1 away from each other, or a rise of 1 and over 1. And we're going to connect these with a line here, as neat as possible. We're going to put an arrow on the end. And then we're just going to make sure we indicate this as the graph that is y is equal to the original function f of x. It's really important we do that, just so we don't confuse it there. Okay, now what is the equation here? Well, to figure this out, we could use either method. We could use point slope form or we could use slope intercept form. What I'm going to use is just slope intercept form to state the equation because we have our clear y-intercept. Y is equal to the original f of x, which is equal to mx plus b. What I'm going to do is fill in my slope. My slope, if you realize from here, to go from any point to at the next point, you go up 1 over 1. And so let's make sure we annotate that here. I go up 1 over 1. There we go. And which means my slope or my m value is 1 over 1, which is just simply equal to 1. My b value, which is my y-intercept, occurs down here, and it's at 0 for x, negative 3 for y. So my equation is therefore going to become where we have x minus 3 because we know that in this situation, whoa, don't want to zoom out there, f of x is equal to 1 for the slope, 1 times x is just x, minus 3 because that's our y-intercept, and this becomes the equation here. Now, just in case we didn't do that above, what I want to make sure we do is we highlight the original equations for these two as well. So I'm just going to make sure I do that before we move on. And then with this one here, again, the major critical points you're going to be looking for whenever you do these is y-intercept, invariant points, and slope if possible. Now, if it's a quadratic, it's going to be a little different. So for these first two, slope mattered a lot. For the next two, slope isn't going to matter as much as we're going to need to solve for the a value like we did in the previous units, like quadraequations, quad functions, all that other good stuff. Okay, let's cycle over to example 3 here. Now, we see these more complicated type of graphs here, and we're like, whoa, there's a lot going on. What we want to do right away is we want to identify a couple points that will help us start to sketch the graph. Those points being, if we look at this one here, they give us a point at 0 and negative 0.25. Well, if we take the reciprocal of that, so I'm just going to make sure I note this off to the side as a point, we have a point, and I want to make sure I kind of avoid this here. We have 0 and negative 0.25, which is the same as negative a quarter. If I take the reciprocal of that, that will give me 0 and negative 4. So if I wanted to, on my new graph, I can go down to 0 and negative 4, which will put me roughly about here. Now, what I want to do is I want to identify all the invariant points. All the invariant points occur when it's at plus and minus 1 for y, so here would be the first one. The second one is going to be up here for positive 1. For positive 1 on the right-hand side, it will be here. And then for negative 1, it's going to be right here. Now, how does this help me? Because if I know that these points exist, whether they are on the original or the reciprocal function, then that means they can be connected with some sort of line that makes this function. Now, I'm going to connect this through here in the following way. I'm going to start down at our vertex, which is representative of this 0 and negative 4, and I'm going to connect it through in the following way. It's going to go up, it's going to go through the points, and then it might continue up this way. Now, we could get very specific with these points if we wanted to. We could even we could calculate our slope, and not our slope, but how much it increases by, and then use that to get more specific values. But with this one, as long as we have our invariant points plotted, and then we have our vertex point plotted based on this graph, we're good. And again, you can approximate the shape in the following way. If you know that we have on the reciprocal function very low values for y, then the reciprocal is a high value, so it goes up here. If we have a very low value for it down here, so somewhere about here, the reciprocal of that is going to be a very high value again. And we look at this and we want to continuously be thinking about it in the following way, where it's always this trade-off. It's if it was a low y value on the reciprocal of that would be a high value. If it's a high value, it becomes a low value on the original graph, and vice versa. We can go backwards and forwards with that and saying they're always going to be opposites of each other in terms of the y value on the original will be the reciprocal or aka lower than the y value on the new, and then opposite to that as well. Okay, so here's our original graph, but we need to know something more specific about this before we actually continue forward, because we've sketched it on here. We're like, okay, that's fair enough. We've provided a sketch here, but we actually want to figure out what is this specific equation. If you remember from previous units when we dealt with quadratic equations, we were always missing the a value because it was the vertical stretch factor, or how far the graph expands horizontally to the left and right or condenses in vertically. So what we're going to do is we're going to go like this and say, well, point number 1, we're going to write this in as the following. We know that we have the form y equals a x minus p all squared and then plus q. Now, what relevant information do we need? We need this point down here, which is the vertex. And so I'm going to make sure I include that here. The vertex was at 0 and -4, which was actually written off to the side here, but I thought I would just include it on our graph. The other thing we need is just some arbitrary point that's on this graph, and that other point can be found pretty much anywhere for the most part. But let's say we take our x-intercepts, because those are very valid points. In fact, our NPVs are a great point to use. So I'm going to put a dot here. I'm going to put a dot here. The NPVs are these lines in which the reciprocal graph kind of diverges away from. Let's write in those points here. This one is going to be at 2 and 0, or 2 for x, 0 for y. This one is going to be at -2 and 0. And now that we have some sort of x and y, which could be either one of these, it could be the 2, 0, or -2 and 0, and we also have some sort of p and q, which is what this is here, then we should solve for the a value. Now, let's go up there and do that here. So we're going to write it as y is equal to, y being 0, is equal to a, x value, which is 2, minus the p value, which down here was 0, so there's no left or right shift. We'll write that in. And then the q value was -4. Now, we expand this. 0 is equal to a, 2 squared is equal to 4, minus 4. We add the 4 to both sides, giving us 4 equals a times 4. We divide both sides by the 4, which is going to be taking away the 4 from the right-hand side and moving it over. And we end up getting that an a value is equal to 1. Now, again, for some of you astute students, you might be like, wait a minute, if we got a equals 1, why did we even solve for it? We need to make sure that this is accurate to the sketch and even to the function required. And if the a value has like a 1/2 or a 2 or something like that, then it has a vertical stretch factor, and we definitely need to account for that. So now we're going to say, therefore, the function we're looking for, or that original f of x, is, we're going to write this as our same function as the original, just without the x. It's going to be x squared and then -4. So kind of a simplistic one. And we should kind of predict this because there was no left or right shift in the vertex. So according to our first units, we'd look at this and say, because there was no left and right shift, it's not like we're going to see anything attached to this x. And then because it went down from the x-axis, it should be a negative value for the q, and we're satisfied with this. And again, you always want to solve for the a value. That is a very, very important step. Okay. Now, let's continue down to this example here. We have an example that looks quite similar, actually. It just looks like it's almost the mirror image or the flip of this. So what we're going to do is we're going to plot out very similar points in terms of like the important points that we want to look at here. And I'm just going to pull the calculator over to the other side so it's out of the way. We're going to write this as the following. If we know that the x is 0.5 and the y is 0.2, in fraction form, I think it's better to see it in fraction form. So I'm going to write it as, we have our 0.5, which is 1/2. We have 0.2, which is equal to 1/5, and they're both positive. Now, if I take the reciprocal of that point, the x will stay the same, but my y value is going to become 5. So let's make sure we plot that in red here. I'm going to go up to 5, where x equals 1/2, and that's going to put me right here. Now, let's label all the invariant points. Our invariant points occur when y equals 1, when y equals -1, when y equals -1, and then where y equals +1. We want to make sure that we sketch that on the curve that's given, and we know that these points will be used on our original function. The other points that will be used on the original are the ones that are at the vertical asymptotes here. And so the vertical asymptotes are these lines that, again, the reciprocal will diverge away from, but for our case, they're going to be valuable points. Now, let's play connect the dots here, and we're just going to go down from our vertex through these points and then continue it this way. And I'm going to just try and neaten this up as best as possible because we want to make sure it's the most accurate it can possibly be. There we go. And then we're going to go down from here and connect the dots and pass through. There we go. Put arrows on the end. And then what we can do here is we can write this as y is equal to f of x. that might be an important step there just to make sure we're identifying this as the original function. If we didn't do that on the one above, I think that might be a good idea here. So what I'm going to do is I'm just going to write this in as y is equal to f of x, where we're basically just classifying this graph and making sure that that's okay. Okay, now what we're going to do is down below here, we know that we now have our original function drawn over top of this, but again, we're missing the a value, but we can use a couple points and we can use our vertex to figure this out. Our vertex was located at 1/2 for x and 5 for y. Our two x-intercept points are going to be at 2 and 0, and our other one is going to be at -1 and 0, like this. And then again, we can classify this point as an x and y. And then we can classify this one as our p and our q. Perfect. Now that we have these two, let's generate what this a value is. So we're going to be like part one here. We're going to make our equation y is equal to a x minus p all squared plus q. We're then going to plug in our x and y being 0, which is equal to a, x value, which is 2, minus the p value, which is 1/2, all squared, and then plus q, which is plus 5. This is going to give us 0 is equal to, well, if we take this, we're going to keep the a out front for a second. If I write this as 2 minus a half, 2 minus a half is the same as 3 over 2. So maybe I'll start there. 3 over 2 squared plus 5. This is going to be 0 is equal to a. 3 squared is 9. 2 squared is 4. And then this is plus 5. I'm going to subtract the 5 to the other side, making this -5 is equal to a, 9 over 4. If we multiply both sides by 4, 4 times 5 gives us -20, which is equal to a times 9. And then lastly, we're just going to divide both sides by the 9. And if we look at 20 over 9, it's not going to reduce, unfortunately, so we get a is equal to -20 over 9. And from unit 1, this should totally make sense we're getting a negative a value, because if it faced downwards or it was reflected downwards, there was a negative a value. So therefore, here's what our takeaway is. Therefore, the equation is equal to -20 over 9 for the a value. The x was x minus 1/2 because it was shifted by a half to the right, all squared, plus 5. There's the equation for this graph, and we would be completely satisfied with this one here. As long as we plotted out each point, we're thinking that this is all good. And again, you don't necessarily want to use decimals if you don't have to. So try to keep things in terms of whole value numbers, because this is going to be our nicest form here. Okay. Now, if you do decimals, don't worry. I won't take off marks, or, unless it's specifically said otherwise, but for most cases, it's going to be okay. Now, what you could do on these graphs if you really wanted to, and I'm just kind of backtracking to this, is if you look at both of these ones where they're the quadratics like this, if it helps you to recognize and draw in the vertical asymptotes, you can. I don't know if that would help us much in this case. Like, it might just be more of a distraction than anything. But if you wanted to draw in your vertical asymptotes, just as a way of seeing like what these reciprocal graphs are avoiding, that would be okay. And what I'm doing here is I'm just going to rewrite the y equals f of x in here, just so that it is on the left-hand side, just like it is on the above graph. Okay, perfect. Now, we've seen how we can generate graphs using the quadratics form. We can also see how we can make them out of our linear graphs. And again, they have these very unique shapes. When we talk about reciprocals of quadratics and reciprocals of linears, they're pretty easily identifiable in terms of like which is which. They just require a bit of practice to understand. And then all of the stuff in terms of how we solve for the equation is directly from our first units. So we're actually very familiar with all this at this point. Okay, let's shuffle to our one application problem, and it's the following. So we may be given some sort of reciprocal function that can be solved using some sort of graph in the following way. Intensity given by I in watts per square meter of a sound equals 0.004 multiplied by the reciprocal of the square of the distance in meters away from the source of the sound. Write a function I in terms of d to represent this function. This is just a very wordy way of saying the following. We have intensity, which I'm going to use a black pen for this one. Intensity is equal to, they said it was 0.004 multiplied by the reciprocal. As soon as they say the reciprocal, it's a fraction of that, the reciprocal, or 1 divided by the distance squared, or d squared. Okay, now if we know that this is the case, what I would encourage you to do, as soon as you get a decimal like this, let's just type it in and see if we can get a fraction. So 0.004, math frac, we get the fraction of this, it's 1 over 250. So what I can do is I can now write this equation in the following way. I can continue this below and be like, it's 1 over 250 multiplied by 1 over the distance away from the source squared, and then this will give us an intensity formula, which is equal to 1 over 250 d squared. And maybe just to keep this neat here, I'll maybe do this off to the side. So I'll go maybe a little bit to the right here and be like, if we continue this here, it's going to be that, and maybe we arrow over just to be exact with it. Intensity is equal to, we have 1 divided by 250, which is 0.004 as a fraction, d squared. Awesome. So now we have some sort of function of I in terms of d. Now, what does this represent? For those of you that are physics people, or have talked about this in maybe biology, this is what we call a rapidly decaying or exponentially decaying function, where the further you get away, it ends up exponentially decreasing the intensity. And in physics, we talked about this a lot in the force unit, or in dynamics when we talk about planetary motion, where like the further you get away from something in terms of the radius between the two masses, it exponentially decreased the force of attraction. This is no different. The intensity of an object, or the intensity of this experienced light in this situation, is decreased exponentially as the distance increases. Now, let's make sure we plug this into our graphing calculator in the following way. In y1, instead of 1 over 250d squared, you're going to type in 1 over 250x squared. Perfect. And then what we're going to do for our x min, max, and scale is we're going to start our min at 0.1. We're going to go to a max of 1, and then we're going to put our scale to 0.1. And we're going to do the exact same thing for y. We're going to write this as 0.1. There we go. Actually, no, we're going to go all the way to 0. Then we're going to go up to 1, and we're going to have a scale of 0.1. And let's see if this works, because it should work, and then I can give you kind of the explanation around it. But I just want to double check this is all good. So in y1, let's clear out all the other stuff we might have, because we might have some other reciprocals in there. We're going to go alpha y equals 1 divided by 250x squared graph. Now, we see something that's like very, very broad scale. It's very zoomed out. So we're going to go to our window, and we're going to clear out this and say our minimum is going to be 0.1. Or in this case, I actually think it might make sense to even have it as 0 for the most part. So maybe if we put in 0 there and we adjust it, make this 1, and then make our scale 0.1. For the y minimum, I'm going to make this one 0. I'm going to make our maximum 1, and then I'm going to make my scale 0.1. Graph. There we go. That looks really good. So what I'm going to do is I'm just going to adjust this x value for the x minimum to be 0. Okay, now that this is our graph, let's just do a rough sketch of what this looks like. It doesn't have to be extremely accurate, but just enough to kind of get the picture here. So it kind of starts really high and then it collapses down here. And oh, it might not give me the best graph if I do this in the notes here. Yeah, I'm just going to freehand it just so that it becomes as accurate as humanly possible. Okay, perfect. And then it kind of flattens out or plateaus this way. And we're going to put arrows on the end because it can technically go both ways. Okay, so this is the graph, and we have a domain that's greater than 0. Perfect. And actually, because they say that the domain is 0, yeah, let's make this 0.1, because if the domain specifically has to be greater than, in the inequalities unit, we knew that if this was strictly greater than 0, then we couldn't include 0. So we're going to make it just something slightly greater. Awesome. Okay, and again, why did we say it's greater than 0? And I should probably explain this and connect these two here. The NPV, or our non-permissible value, is where x cannot equal 0, or in this situation, the NPV, based on the actual context, is where the distance away from the source cannot be 0. Because if the distance was 0, it would mean you are the object, and I don't think the distance away from an object is the object. You wouldn't say that the light source is the distance away. There's just, it doesn't make sense for this. You have to at least be some infinitesimally small distance away from a source of light, or else you would be the object itself, and we don't want to have that. So that's why we need to make sure that our domain is strictly greater than 0. Okay, now from here, what is the intensity of the car horn if you're standing 5 meters away from the car? Essentially, this means if we have an X value of 5, what is the intensity, or what is the overall I value? So we're going to write this in as I is equal to, I'm just going to rewrite the original formula, 250. This is going to be distance squared. We're going to plug in the value. So this is going to become, let's maybe do this vertically, 1 divided by 250 times the distance, which is 5 squared. This is the same as basically saying 1 over 250 times 25. And then this is going to give us an intensity, or an I value. Let's make sure we have this here, is equal to, I'm going to pull out the calculator, do my fraction, and I'll have to quit out first. So fraction, 1 divided by 250 times 25. And this ends up giving me 0.00016. If we click math fraction, this gives me 1 over 6,250. So maybe what I'll do is I'll record both. I'll record the decimal first, 0.0016. And then I will also record this using the 1 over 6,250. Now, I just want to make sure I get the units right? Because if this is a written response, or if this is something that we're responding to, we want to make sure we're doing it in an accurate way. So the intensity is measured as watts per meter squared, or how many ever watts per given square meter. So we're going to write this as a watt per meter squared. And we'll do that for both answers here, for the decimal and our fractional form. And I'm going to highlight both because with this situation, I don't think they specified which one they wanted. I'll go back up and just double check that very quickly, but it didn't look like they specified. Okay, awesome. This is where you're going to want to get practice with sketching these things out in terms of sketching the original and then being able to build the equation, not only for linear, but quadratic functions. And then being able to do problems like these ones where they may get you to consider reciprocals in terms of some sort of application to that, and what that might look like using reciprocals to represent relationships graphically. Okay, here's your practice problems. Good luck with the practice, and then see me if you need help.